for CS151 Computer Science 2, and this corresponds to Chapter 8 of the Malik textbook. So we'll start off with the data types that we've seen so far. And the first are simple data types. These are single values. Examples are int, char, double, and bool. You've probably even seen short and float, long, long double, etc. Those basically describe a single value. Structured data types are collections of simple data types that describe more complex structures. For example, structures in classes in our object-oriented programming overview. Now we're going to look at pointers. And a pointer is a variable whose content is an address and is therefore said to point to a memory address. Philosophically, this may seem a bit strange, and there's an old Zen saying that says, "Do not mistake the pointing finger for the moon." So, the pointer is just showing you where it is in memory. And the other one is a map of a place. It's not a place itself. It's just a representation of the place. And what I have here is Beck's map of the London Underground, which is an interesting topological map, and the distance between the various stations is invariant. Irrespective of the geography involved. And it's a really interesting map to look at. The London Underground Authority didn't like it at first, but it was very broadly accepted by the general public, and it's become a classic map for its topological properties. And it was actually based on circuit diagrams of all things. So back to pointers. A pointer is the memory address of a variable, and a computer's memory is divided into bytes, and a pointer indicates the address where the variable is held in memory. For example, it could be 1007, although addresses tend to be a bit more complex than that. Your first thought is probably, this seems a little bit strange. And the second thought you should have is you've already used pointers, and you've used them in the form of call by reference parameters, where you were pointing back to the original variable in main and modifying that variable. So you can declare pointers by doing a *p. So basically you hold it in a variable, but it's not a variable of just type int or double. So to declare a pointer that points to a double, I would do double and then *p, and that declares a pointer p that can hold pointers of type double. Each variable type requires a different pointer type, but that's pretty easy, and that's just done by placing an asterisk at the beginning of the variable name. So what do you think the following does? We have int *p1, *p2, v1, and v2. And this one's a little bit tricky. P1 and P2 end up being pointers, and V1 and V2 end up being ordinary integer variables. So you can kind of mix and match them, and that's one of the dangerous constructs in C++. The other operator worth noting is the ampersand operator, which gives you the address of the variable. You can then assign that address to a pointer variable. So I can do things like say P1, which is a pointer variable from the previous slide, is equal to the address of V1. So I can now either call V1 or I can call it *P1. And when used that way, the star operator is called the dereferencing operator, which gives us the value stored at the memory location pointed to by P1. So the semantics of those operators are a little bit tricky, and we're going to have a lab that'll clear that up a bit. So for this segment of code, what do you think the output will be? We start with V1 as an ordinary variable. That's equal to 0. P1 is equal to the address of V1, and then I do *P1 is equal to 42. That changes the value pointed to by P1 to 42, and since P1 points to where V1 is stored in memory, it also changes V1. So the result will be 42, 42, and that's the answer to life, the universe, and everything else. You can use the assignment operator to have one variable point to another. So P2 is equal to P1. That has P2 point at where P1 is pointing at. It's not the same as *P1 is equal to *P2, which changes the variables that the pointers are pointing to. So P, *P, and ampersand P are all different. Although if P were a pointer, you probably wouldn't use the ampersand P. What happens with equality? Well, if P1 is equal to P2, we can start out in the upper left. P1 is points at a storage location that holds 84. P2 points at one that holds 99. When I say P1 is equal to P2, P1 now points at the memory location that holds 99. Star P1 equals star P2. That basically says that the value stored in P1 is equal to the same value stored at P2, and that puts a 99 in that box that used to hold 84. So initializing pointer variables, they need to be initialized if you want them to point at anything. You can do this with either the value 0 or null. So you can say P is equal to null and P is equal to 0, and those will both do the same thing. They'll be pointers, but they won't necessarily point at anything. In C++11, you can use null PTR as a value for initialization. So this leads us into dynamic variables. And basically a dynamic variable is a new nameless variable that we can get from allocating new memory. So we can do things like P1 is equal to new int. That will give us a new variable. The new variable is referred to as star P1, and it can be used in any place an integer variable can be used. So I could do cn star P1 to get a value to store in P1. I could do an assignment value to add 7 to the value stored at P1. New operator produces this new nameless variable, and these are called dynamic variables because they get declared and allocated as the program runs versus static variables that get declared at compile time. So the area of the memory where this dynamic memory comes from is the free store. New dynamic variables use the memory from the free store, and one of the things to be careful of is if all the free store is used, then calls to new will fail. Unneeded memory can also be recycled, and this is a process known as garbage collection. So when variables are no longer needed, they can be deleted and the memory can be returned to the free store. Unless the program is terminating, you should delete them, and probably even if the program is terminating. And recycling is important because if you do run out of memory, then you will usually get some type of unhandled exception and the program will crash. And I'm sure everybody's had an experience with that at least once in their life. So to get rid of this memory, use the command delete, and that returns the memory from the dynamic variable to the free store so that you can reuse it. And basically, delete P destroys the dynamic variable pointed to by P, so the value of P is now undefined. You could set it equal to null or have it point at something else. When you delete a pointer variable, the dynamic variable that points to is destroyed. The pointer is now undefined, so you don't know where you're pointing. If another pointer variable was pointing at that same dynamic variable, if they were both pointing at the same place, then it too is undefined, and that's called a dangling pointer, and that's another dangerous construct that we can find ourselves running into. Typedef, you can basically define a pointer type so that you don't have to remember that tricky asterisk. So typedef basically allows me to rename something in C++. So typedef int star int ptr. So now int ptr is the same as int star. You can also use a pound define as a preprocessor directive if you like. So int pointer p and int star p are basically the same thing. You can also use typedef to create some pretty obfuscated code. So, for example, I could rename double as kilometers, and then every decimal value I wanted to declare I could put as kilometers, even if it was referring to kilograms. You can get quite nasty with typedef and make a pretty unreadable code. Advantage is obfuscated C code. If you want to enter the International Obfuscated C contest, that's great. And typedef will definitely help you there. For pointers, it avoids that omitting an asterisk mistake. And when you use call by reference, you don't need to have both a star and an ampersand. For example, you can use typedef int star int pointer and then pass int pointer ampersand as a reference without using the star. Another use for dynamic variables is dynamic arrays. And here, what we had to do in CS150 is estimate the size of an array that we need. overestimates are the best, but you often waste memory. And if you underestimate how much memory you need, the program won't work. So if I said, hey, my class roster is always going to be a size 22, and I end up getting a 23rd student, then my program won't work. On the other hand, if I said it was 100, and I end up with only 13 students in the class, then I'm wasting 87 pieces of memory corresponding to the student objects. So, it's tricky if you're using static arrays, but dynamic arrays are great because it's not specified when I write the program. And so that's how we get around those partially filled arrays. And you may have noticed previously that array variables are actually pointers to the first memory location, which is why we pass the size separately. So, again, because they're pointer variables, what we can do is we can say typedef int star int pointer p, and then I can have p point at an array of size 10, and then p would point to the first object in the array. A is equal to P, that's highly ill-advised and generally illegal on most compilers. And, if you think about it for a few seconds, you'll figure out why that one's a pretty bad construct. And so dynamic arrays, basically we declare a pointer, in this case a double, call it P, and then say P is equal to new to allocate that memory from the free store. And it's of type double, and we're going to make size 10. Or we could even make it a size of a variable that the user provided us. The pointer type that you use for a pointer to a dynamic array is the same as one for a single array. And the pointer to the array is actually a pointer to the first indexed element. So, again, you could use this to get input from the user. Here we're asking for the number of elements and then declaring a new array of doubles that is the size of the number of elements specified by the user. Can you do this with structures and classes? No problem. Just change the typedef. Don't arrays take up a lot of memory? Yes. And what happens when I don't need them anymore? Well, you just use delete square brackets A, assuming that A is your dynamic array. What you don't want to do is just use delete A, because that will delete only the first one, and you'll be left with a memory leak. You can also perform arithmetic on pointers. It works on addresses, not on the numbers. So if you do +1, it moves to the next memory location that would hold that type. It gives you an alternate way to manipulate arrays. So for example, if I had an array called D and I wanted to move through that array to output each value, I could see out the dereference value of D plus I, and then use a space after that. And that would output every value of the array. You can't do multiplication and division, but you can do subtraction. And subtracting two pointers sees the number of index variables between them. But you have to remember to keep both pointers inside the array. You can also use increment, plus plus, and decrement. And you can also compare for equality using the double equals, but that only works for the memory addresses. You can also have multidimensional dynamic arrays, and these are a bit tricky because what you're doing is creating an array of arrays. So you create a one-dimensional dynamic array of pointers of type int star, and I can again use my convenient typedef command here. Int star is int array pointer, and then I need to make another pointer to m, which is a new dynamic array of int pointers of size D1. And then I can go through and allocate for each element in the original array of pointers, I can allocate a new dynamic array. And that gives you a D1, D2 array. Malik has an alternate way to do this on page 844 if you're interested. So this is what the process would look like here. M is a dynamic array of pointers, and each one of those pointers points to a new dynamic array that we allocate using that new command. And it's kind of tricky to think about it initially, so what I recommend doing is just going from the code on the previous slide, and then as you use it more and more, it'll become more of a comfortable construct for you. And cleaning up is also tricky. You need a loop to clean up the memory because you're going through the original array, and for each one of those, you're deleting the dynamic array that's pointed to by that. And then finally, you clean up the overall dynamic array. So next time we'll do a little bit of a lab, and that'll get us more familiar with these constructs. Thanks for watching.